I'd be willing to make a bet that at some point in the last few days you took a photo on your phone. If not a photo, then definitely a screenshot of something you saw on the internet that you really wanted to remember, and will no doubt never look at again. Last episode we covered some of the basics of how a computer converts the visual information of an image into binary, a series of ones and zeros. But how does the computer then store that complex binary sequence so it can be accessed later? Well, that's what we'll be discussing in today's episode. Brace yourself, it's going to be a big one. When you tapped on the Photos app on your phone to have a look back at your photo, what you actually did was tell your phone, a small computer, to run the program it has stored that executes a series of processes to give you access to your photos. This is possible because your phone is able to store data on it. But the very first computers didn't have their own storage to hold programs for easy repeat use, let alone any other data. And a computer needs to have a program to run in order to do anything. So if we take a look at the massive house-sized ENIAC computer from 1947, it took up to 2 months to set up a program to run. This potentially involved the use of over 2,000 rotating knobs and around 3,000 switches. There is no doubt the programmers of the day dreamt of having some way of storing a program for future use once it had been set. This is where Hollerith's punch card system we mentioned a couple episodes ago came to the rescue. The first form of storage for computers came in the form of pieces of cardboard with holes in them called punch cards. A computer programmer would first write a computer program by hand and then would use a punch card machine to convert the program into punch cards. These punch cards could then be fed into the card reader in the correct order to run the program. The largest punch card program created was from the 1950s Sage air defense system. It needed an incredible 62,500 punch cards to run, the equivalent of around 5 megabytes of data. Now consider this, if one of those 62,500 cards was lost, or inputted in the wrong order, the program wouldn't work. This is a process with a lot of potential for error, and a lot of limitations, including physical storage. This entire warehouse of punch cards contains only 4 gigabytes of data, the equivalent of a tiny flash drive today. The key question that needed answering was this: how can we store a binary sequence for later access? And one of the first solutions that didn't involve punch cards used a similar concept to one we are already familiar with from the invention of the telephone. The key innovation came from a man named J. Presper Eckert, one of the creators of the enormous ENIAC computer we discussed earlier. His solution for computer memory involved filling a tube with mercury, with a transmitting speaker at one end and a receiver microphone at the other. The speaker could send a pulse through the mercury that would then be converted into an electric signal by the microphone at the other end. In this way, a sequence of pulses could be sent through the mercury that recreated a binary on-off sequence. If the electrical output of the microphone was then sent back to the speaker via an amplifier to compensate for any signal loss, a perfect loop could be created that maintained the binary signal, thereby storing the data as long as the power supply to the circuit was maintained. Who would ever have guessed that the first proper computer memory solution would be to store data in sound waves? A remarkable solution. But despite this, there were many limitations to this process. One of the major ones being that this data could only be accessed sequentially, meaning if you wanted to access a particular piece of data, you had to wait for it to loop back round again, leading to it being called delay line memory. It was also an example of what would come to be known as volatile memory, meaning it would only be stored for as long as power was maintained. The solution to this limitation was found in an invention called magnetic core memory, which came into use in the 1950s, and again draws on some concepts we've discussed previously. The basic component of this involves a small magnetic ring or a core that then has a wire attached. When a current flows through the wire in one direction, it sets the magnetic polarity of the ring in the corresponding direction. When the current flow switches to the opposite direction, the magnetic polarity of the ring switches also. So in this way, it was possible to store one bit of binary data, where one polarity equals a 1 and the other equals a 0. The big kicker here is that the magnetic core is able to store this polarity even without a power source, meaning that this is what we would call non-volatile memory, or the kind of data storage we're used to today, where you can switch off your computer and walk away and all your saved data is still there. Now this ring only represents one bit of data, So in order to store larger amounts of data, these were arranged into grids. This then allowed another huge leap, which was that this was not sequential access like the previous delay line memory. Any bit could be accessed when needed without waiting for a sequence to loop, giving birth to what we call random access memory, a huge necessity in allowing computing to be fast and efficient. But there was big physical limitations, with the amount of data that could be stored limited by the number of tiny magnetic loops that could be assembled into a grid within a reasonable scale. Also, a huge limiting factor was that the manufacture of many of these early memory boards required intricate assembly by hand. Magnetic core memory would remain in use all the way into the 1970s, but by the 1950s the next innovation to change the process had arrived: magnetic tape. This came at the hands of J. Presper Eckert once again. He wasn't the inventor of magnetic tape, nor of the idea to use it to record information, as it was already in use to record audio, in particular in Germany during World War II. But he was one of the first to realize its potential to store computer data. It worked by feeding magnetically coded tape from one reel to another, and as it did, it would pass beneath a write head that, just like the magnetic cords earlier, would have a current sent through it that would create a magnetic field. This would in turn set the magnetic polarity for that section of tape, and so as the tape was fed through and the write head alternated its current according to the binary data, the data was recorded on the tape. The huge benefits of this medium was that it was far more compact and had far more storage capacity, and was significantly cheaper to produce. The major setback was that, like delay line memory, it was sequential access. For a piece of data to be accessed, the tape had to be fed through a reader to the right section before reading the data, and so it had inherent limitations on the speed it could operate at. So it may surprise some to hear that despite its age and limitations, the tape format is still in use today for archival storage. It's more secure from cybercrime, requires less energy, provides long-term durability, and has a lower cost per gigabyte of storage than modern hard drives, with IBM recently announcing they had increased the capacity of one tape cartridge to 580 terabytes of data. The innovations in computer storage from the tape drive onwards built on concepts we have mostly already discussed either here or in previous episodes. The floppy disk took the idea of magnetic tape but laid it out flat as a spinning disk, meaning this greatly reduced the time delays of sequential access. This led to the optical disc, also known as the CD and DVD. Again, much the same concept as the floppy disk, only instead of storing data magnetically, it was stored optically, which greatly increased its storage capacity. It did this by encoding tiny little divots into the reflective layer in a spiral pattern outwards from the center. The reader of the disc used a laser to shine onto the spinning disc, and as the laser hit the divots, the reflected light that returned to the reader alternated in time with the changes in the surface, and these alternations created the binary signal. The spinning disk design also led to the creation of the hard drive, which used multiple disks called platters made from a non-magnetic material, then coated in an incredibly thin layer of magnetic material that would then have data encoded on it in a similar process to what was discussed earlier. And the hard drive would be the king of storage mediums, because as technology advanced, it would eventually hold just the right balance of storage capacity, speed, and affordability. Catching up quickly, though, was solid-state drives, which used the transistors and integrated circuits we discussed in previous episodes to store data. And as the capacity of integrated circuits has increased and costs of production have gone down, solid-state drives are now taking over as the preferred format. It's these that are used on your phone, in most new computers and new external hard drives, as the lack of mechanical parts means greater speed and greater reliability. And that brings us up to date with the storage of computer data, which means we are now ready to embark into the internet age. You may have wondered why the first 4 episodes in a series titled The Internet have not yet really discussed the internet. Well, everything we've covered in the last 4 episodes is everything the internet is actually made of. So we have actually been talking about the origins and components of the internet this whole time, only now we'll be getting into it properly, with the process of how it was invented and how it works, so we can understand better how it has completely changed the process of how we communicate.